Hi everyone. So let us continue our discussion on connected spaces. I will try that there is, less echo today, but it is because of, the kind of room I'm sitting in, and I cannot open the door because then there will be lot of disturbance. So let me, like what I have promised, let me, proceed towards that. So I want to first, begin with an example. So example. So let's take fx equal to sine 1 upon x on 0 to infinity. Okay. Or, yeah, it's fine. So what I want you guys to show that graph of f is connected. So what is graph of f? So graph of f is basically nothing but, you know what it is. I'm just formally defining it. X in 0 to infinity. So that's what you have to show. I'm leaving this as an exercise. Okay. Or it's not very difficult, right? See, open interval 0 to infinity is connected. F is continuous. Now you think about it. I'm not giving any more detail. So you have to show that this graph of F is connected. So visualize this graph of F as image of some continuous function. Then you are done, right? If graph of F is image of some continuous function, and if the domain is connected, then this will be also connected. Just that you have to do. So hint is just construct a map from 0 to infinity to GF, which is continuous. So since this is connected, so this will be also connected. Okay, very nice. Let us define another set. Say T to be S union graph of F where S is what? 0 comma y is ranging from -1 to 1. So basically, if you want to sketch this, let me sketch this. Yeah, I may draw very bad, but topology. Oh my God, this is really bad. So like this, it should be graph of sine 1 upon x. How it will be? You know how to plot it. I'm not telling you. Oh my God, wait. Yeah. So this is like this. Oh my God, this is a very bad picture. Let me properly try to draw it. I should use my, then clusters. Oh my God, I'm not able to make a good picture. So let me, reduce the sign of the size of this. Still not. But you know what it is. So please draw it properly. And then along with this line, right? Now I have to, yeah, make it a bit large. Yeah. So along with this. So what can you say about? Just a random question. Is T connected? So think about it for a moment. You may think, oh, it seems to be disconnected because this line on y axis, this graph is actually not touching it, right? So you may say disconnected by just, if you have a look on this, you may say this is disconnected. Please make a good graph of this, picture of this T. Okay. But surprisingly, answer is no. T is connected. No to this. T is connected. So that's what we're gonna show. This is the first aim for this, session. Okay. So to do this, let me do something. Let me have a proposition. Proposition. By the way, this thing you call topologist sine curve. Okay. And this is very important. What you call topologist sine curve? Let me, tell you. Actually, just the point, okay, I'm not defining now what is a topologist sine curve, but yeah, something like this you call it topologist sine curve. Leave it what it is. Yeah, it's basically the graph of this union origin. Okay, so the proposition is okay, so capital A be a connected subspace of X. Say A is sitting inside B, which is sitting inside A closure. Then B is connected. So in particular, closure of a connected set is connected, right? So this is what you have. Now, before proving this, the proof is not very hard. So before proving this, so if you see this GF closure, if you see this is nothing but this T. This is an exercise. And graph of this function sine 1 upon x is connected. So its closure should be connected. So this space, what you may think for a moment, oh, it's like two things. It's disconnected. But in fact, this is connected. Okay. If you know already, but we will learn something called path connected, we will show that this is not path connected. So your visual intuition is there should be something joined always. You know, that that intuition is being challenged here. So this is one of the most beautiful example according to me. Uh, a simple and very beautiful example. Okay, to show this, actually I can give this as exercise, or maybe let's have a proof. So let f from b to d, d along with 2 to the power d, meaning discrete space, be continuous. To show, what you have to show? To show f is constant. Because if f is constant, we are done, right? This is the equivalent criteria for checking a space is connected or not. Okay, very nice. So, shall we proceed? So now, A is connected, right? So this implies f restricted to A is constant. Okay, very nice. Now let us see what is A closure in B. This has to be A closure intersection B. Am I right? What is A closure intersection B? This is nothing but B. Okay. So now let us see what is f of B. So what is f of B? F of AB closure, and this will sit inside f of A closure. Y or Y? This is a question mark for you guys. And this is nothing but FA, right or wrong? Think about it. So what this will imply? See, F is constant on A, right? So this will implies F is constant on B. So these Y things are your exercise. So basically complete this proof, huh? Complete the proof. This is very important, huh? Please do this. Why FA closure is FA, okay? And why F of A closure, A closure in B is contained in FA whole closure. So definitely you have to use two things. One is this continuity you haven't used. Another is this thing you haven't used. And this A closure in B is A closure intersection B. This I have given you as an exercise, if you remember. So you see, this is a very beautiful result. And we have this beautiful example with this result. Okay, so now finally, I can come to the theorem which I wanted to prove. So we will use the above result to prove this theorem. So theorem is theorem. So X alpha, alpha, these are topological spaces. Be a family of topological spaces X alpha are connected, all basically are connected if and only if product of X alpha is connected. So that is what we are gonna show. That is what I said, that this is the plan for the today's lecture. Okay, so how to prove it, guys? One part is very obvious. See, the converse. Prove. So consider the projection map. That's all. So on the alpha coordinate, so this is continuous for every alpha. So what it means? So this implies x alpha is, I'm doing the reverse direction, okay? Connected. Why? Because the continuous image of connected set is connected, space is connected, and you have assumed that product of x alpha is connected. Very nice. Now let us do the another part. This is a bit tricky. This is not that obvious. So let's see what we can do. Huh? Okay. So let Z belonging to product X alpha. So this Z is some point Z alpha, alpha in capital lambda, be a fixed point. Now, what fun we are gonna do is let Y be the union of all connected subspaces or subspaces of product X alpha containing small z. Meaning, it is the union of connected subsets, and any two subsets have non-empty intersection. At least z is there. So you know our theorem which we have done last time. Then if you have some sets, some family of connected spaces such that all are pairwise disjoint, then the union is connected. So this implies Y is connected. Okay. Now, claim. This is a very fun proof. Claim Y closure is nothing but product Excel. If you do this, then you are done, right? Because we are done. Okay. If we prove this, then we are done. Why? Let me just verbally say. Okay. Then let me write. We are done. Why? Because Y is connected, it implies Y closure is connected. That's what we have proved above. So now the job is to show what? That Y closure is equal to product X alpha. Meaning Y intersect with every open set in product X alpha, right? This is because of X belongs to A closure if and only if every open set containing the point X intersect your A. That characterization. So you see everything what we have done, we are using, and this is how the topology is gonna be. Okay, very nice. So let B be any open set in product X alpha. Now, how B look like? You remember? So this will be some alpha 1 inverse U alpha 1 intersection alpha 2 inverse U alpha 2 B alpha K inverse U alpha K where U alpha i's are open in X alpha i's for every I in 1 to K, right? That's how we have defined, no? Okay, now let me define some sets. Here's the tricky part. So let us define something called even. So what is even? All such x in product x alpha such that there is a condition on the alpha coordinate, that is z alpha, for every alpha different from alpha 1. Similarly, what I want to define E2, all element in product x alpha such that x alpha is equals to z alpha for every alpha different from alpha 1, alpha 2. So similarly, what will be our EK? EK would be collection of all elements in product X alpha such that X alpha is equals to Z alpha for all alpha but alpha 1 to alpha K. That's what we are doing. Okay. And let me do some modification. So what about at alpha 1 and alpha 2? Let me specify that also. Okay. So let me do some change here. So let U belongs to B. Say U is equals to some U alpha I. Okay. So what change you do is add this, alpha I. You define it to be U alpha I equal to 1, 2. So similarly, this whole set is my E2. So similarly, what will happen here? And X alpha I is equals to U alpha I for every I in 1, 2. Say, or maybe just do it for I equal to 1. Leave the other component that will work. Yeah. So yeah, this is a bit tricky. K minus 1 up to K minus 1. So here I have 1. So no component I am restricting. Here, in other words, X alpha 1 should be U alpha 1. Okay. Now, what I want you guys to observe is Z belongs to E1. Observe. I'm not doing that. You have to do. Okay? And something more. U belongs to En. Okay? And something more. Ek. How many I'm taking? K. And Ei intersection Ei plus 1 is empty for every I running from 1 to K minus 1. That is the another fact. Okay. So these are some things. Okay. Now, another thing I want to you guys to observe that this EI is nothing but this is homeomorphic to X L5. Homeomorphic. Meaning EIs are connected. So this implies union of EI is also connected and Z is in the union. Oh, meaning this is contained in Y by definition of Y because Y is the union of all connected set containing the point Z, right? Okay, very nice. So U is in Y, right? Because U is in union. It is in EK. So U is in Y and U is in where B also. So this implies Y intersection B is empty or non-empty. So you see, we have a basic open set. We have chosen a point in that and we have constructed a sort of connected set. Yeah, using that which contains Z. So it has to be in Y. So now finally Y intersect with B. That's what we wanted to show, right? If Y intersect with every basic open set, then we are done, right? Then Y closure is nothing but what? Um, your product X-alpha. So this implies product X-alpha is connected. So yeah, there are some things to observe. So this is your exercise. So I'm gonna leave, simple things to verify. So I think that's all for today. And what we can do, we will continue the topic. We will study something called components or precisely connected components. So we will, take on this discussion further. Thank you for your attention.